So in general, we know that sea level is rising, so presumably you can also measure that using altimetry.
Exactly. And we have been measuring this basically since 1991, with the first European remote sensing satellite, EOS-1, was launched in 1991, shortly followed by TOPIX Poseidon. And I said already, TOPIX Poseidon is this reference mission. That's one of the better altimeter satellites.
So we've got time going along the bottom, 1991 here, and today over there.
And today, yeah, at the end, yes. I actually made this plot last week, so it's really up to date. It has even a little bit of JSON 3 in there already.
And this is global mean sea level, so you've picked a reference 0 here.
Yeah.
So this is not because sea level is negative, but because compared to the year 2000, it was a bit lower. So it was 30 millimeters lower, 3 centimeters lower in 1991 than it was in 2000, and then this.
And now it's almost 6 centimeters higher than in 2000.
So that's a big change.
Yeah, we have raised sea level globally in the mean by 8 centimeters in just this period. So in the period that I was working on this, we have increased sea level by 8 centimeters. Now, here, this picture on the back, of course, we have dunes, but not all cases we have land masses with dunes. We have islands that barely rise above the sea level, and then 8 centimeters can already be quite significant. Don't forget, on top of it are tides. When you normally would just survive a high tide, now you might not survive a high tide anymore.
And this rise is remarkably consistent, isn't it?
Yeah, it is remarkably consistent. Of course, there are some variations, and some of the variations we actually understand why that is. They are due to El Niños. For example, here we had a large La Niña and El Niño variation, and you see that still in the mean. And there is still a consistent trend of 3 millimeters per year. So every year it's about 3 millimeters. Some years are faster, some years are slower, but on average it is 3 millimeters. So don't focus on just one period, because there are variations, long-term variations. You can see sometimes as much as a decade long variations, but the trend is very clear. And what is also very important is that all the altimeters basically show the same.
And these are all different, these are different satellites, so every colour on here, so the red one here goes from there to there,
yeah,
and then the yellow one kind of overlaps with it, and so they're overlapping data sets from different altimeters.
Yes, exactly, and that overlap is so important, because with the overlap we can compare these satellites very well. Now, if they are running in the same orbit, meaning that they overfly the same track, like JSON 2 and JSON 3 are now at this moment, we can do that very accurately. In other cases it's not as easy, but still, because many missions, as you can see, have sometimes many years of overlap with others, we can do a very good job of aligning all these lines very well, and understand, of course, when one is different from the other. And of course, if you have 3 at the same time as one is the outlier, we usually can figure out, why was that? And sometimes it's instrumental, sometimes it's something that we did in the processing that was not done correctly. So we learn, and every mission learns from the other. But the overall picture is a sea level rise, and a very, very consistent one.
So an 8 centimetre change in the past 30 years doesn't sound like very much, except that our infrastructure and the way that our harbours are organised and the way that people on remote islands live, for them that's a big difference, because if your tides come that much higher, they could go a lot further inland.
Yes, of course. And it's also not everywhere the same. And as you can see in this image, so here over these same 25 years, you can see the local sea level rise. So we were saying that on average is about 3 millimeters, so then you're more or less in this orange area. But there are clearly areas where it's darker orange and red, and there the sea level is actually rising more. In areas in the Indian Ocean, it's rising as much as 5 millimeters per year. Here in the South Pacific, it goes even up to about 1 centimeter per year. So it's not homogeneous, and actually we want to learn why that is the case. Why is there some places goes as more rise than the others? Of course, if you say melting of the ice, you would think that it will distribute homogeneously, which is in fact not exactly the case, because we're changing the gravity field as well. This is going a little bit far to explain that, but also, of course, because of the heating, some places heating is more than in other places. And you see there are variations that have something to do with the dynamics. Here we have a strong current, the Kuroshio, and here we have the Gulf Stream. And both in these cases we see a quite stark difference on either side of these currents. That can mean a lot. It can mean that on either side it's more heating than on the other side. It can also mean that the current is slightly changing in strength or in position.
So this is very important data. If you're living in one of these places, so you might have individual tide gauges, for example, around the coast that said, you know, it looks maybe in this place as though it's got a little bit higher in the past couple of decades. But this satellite data gives you this overview that shows you the big picture, that sea level rise is going to hit some places a lot harder than others, and you can see where those places are.
Yes, you can see that. And if you would plot in your tide gauges, you would of course find them mostly along the coasts, which of course is where it's most important. But you would also find it mostly on the northern hemisphere and not in the southern hemisphere. So this indeed gives you a global picture. Is global picture of what is happening, and not just in the tide gauges. Also, tide gauges can have a problem because you put them on land, and is that land stable? That could as well be changing itself, or the tide gauge might not have been properly embedded on rock, for example. Now, of course, it becomes a little bit more complicated when you start to say, you know, what is the sea level rise? Because indeed, compared to the land, we need to think about, and in some cases is worsened by the fact that the land is at the same time sinking.
And so this is a sort of information that is really useful to policymakers. For example, if a government is deciding whether to invest in flood defences or whether to try and protect a region from the sea or just to let it go, this is exactly the sort of data that is needed very practically by governments and local organisations to plan their future.
Yes, of course, because you cannot deny that these patterns are quite systematic. So if you look, for example, in the North Sea coast, we're actually not that badly off. Still, it is a positive number, so there is rise and we need to take care of it. Also, of course, in the east coast of the United States, where a lot of people living very close to the coast. And exactly in that point where we need to consider that sea level is rising, and you need to build up your defenses, because you have to raise your dikes, you have to raise your levees, as they're called in the southern United States. You cannot just let it go as if nothing is happening. It is happening, and it is very clear, and all these missions show the same thing.